Hello Year 10. Today's lesson is about energy change calculations. I've got 10 examples to work through with you. Each example uses the equations that we've been learning over the past few weeks for kinetic energy, for gravitational potential, for elastic potential, for work done. And you have to use them together to work out various things. What I suggest you do is I've sent you a link to a platform called Desmos. Those 10 questions are in Desmos and you have to answer the questions in there. I would work through this video stage by stage. I wouldn't go through the whole thing in one go. I would work through each question at a time, and then as I'm explaining how to do the question, have a go at the question on Desmos and then submit it. Okay? So just so you're clear, go through each question one at a time. When you're happy that you know how to do it, have a look at it on Desmos, input your answers. You will need a calculator, you may need a piece of paper handy, and then submit your answers on there, and I can have a look at those as you're working through. Okay, so you can go through this at your own pace. That's the beauty of Desmos. Okay, so let's move on to question 1. So here's an example of a girl on a swing. Question 1A says, describe the energy changes. Well, let's take position 1 up here. So in position 1, answer to A, that's lots of gravitational, so I'm just going to call that GPE. As she swings down this way, that changes into KE. So at position 2, here she's got maximum KE, she's moving the fastest. She continues to swing up that way to position 3, where it all returns back to GPE again. And this process just continues to repeat. Now, there is some energy loss all the time, so a little bit is lost because there's friction as heat all the time. Let's have a look at part B. What is the maximum velocity of the swing? Well, now we don't know the mass of the girl, but what we do know is that assuming no energy loss, we'll assume no energy loss in this question. Okay, we can say that the GPE in position 1 equals the KE in position 2. Therefore, M times G times H equals a half M times V squared. You'll see that the M's cancel out. M cancels out. Okay, so what we're left with is GH. I'm going to draw a line over here. GH equals half times V squared. Now we do know all of this information. Okay, so I'm going to substitute in all the stuff we do know. So G is 10. The height there is 0.5. That is 0.5 meters, equals a half times V squared. Half of 10 is 5, equals half of V squared. Therefore, V squared equals 10, because I have to multiply both sides by 2. Therefore, V is the square root of 10. And I'll let you work that out with a calculator. Right, this question is about a roller coaster. We're going to assume that no energy is wasted in this question. Okay, it says there, no energy wasted. A says, describe the energy changes as the car rolls down the roller coaster. So position A, well, it's all GPE, isn't it? Okay, roller coaster doesn't move at the beginning, so it's got no KE. As it rolls down the ramp to B, it picks up some KE, but it still has GPE because it's above the ground. As it goes up to C, well, it has slightly less KE than it did at B, and slightly more GPE. And then as it rolls down to D, all of the energy becomes KE. Okay. B says, what will the effect on the journey time be if the mass of the car is increased? Well, it makes no difference. The mass of the car makes no difference. Here's the reason why. Okay, so for B, we're going to have an energy conservation. Let's consider the energies here. So we know that the GPE at the top, position A, must equal the kinetic energy at position D, because no energy is wasted. Okay, so mgh, which is the formula for GPE, equals a half mv squared. So we can see that there's m on both sides, therefore the m cancels, and we can see that gh equals half v squared. So the speed only depends upon the height and the value of g. Okay, it doesn't depend on the mass. The speed does not depend on the mass. If we make the track steeper from A to B, that has no effect, because the only thing that affects the final speed is the height, okay, not the steepness. Let's have a look at question C. If A is 1.2 meters, well, let's put that information on the diagram. 1.2 meters, that's up to A. And C is 0.9 meters, so let's make that 0.9 in there. What are the speeds at C and D? Well, the height change from A to C, yeah, so there is a height change from A to C, which is 1.2 minus 0.9, which equals 0.3 meters. So as the car rolls from A to C, it becomes 0.3 meters lower. So it's lost some GPE. So the loss of GPE, well, that's mgh. That equals the gain in kinetic energy, half mv squared. M's cancel. So we've got 10 times 0.3, okay, because that's the height difference between A and C, equals a half v squared. So we can work out v squared equals, that's going to become, that's 3 on this side times 2 is 6. So v equals the square root of 6. And this is the speed at position C. Now, you repeat that whole thing there, repeat that. So to work out the speed at D, okay, so speed at D is the same method, except that the change in the height is now 1.2 meters, because it's going all the way down from A all the way down to 0 at the bottom. So the height change is 1.2 meters, and you can work out using the same method what the velocity must be. Okay, let's move on. Okay, question 3 shows a boy throwing a ball upwards. We're asked to calculate the kinetic energy of a 0.6 kg ball when it's thrown upwards with an initial velocity of 2.6 meters per second. Assume no energy is lost. So A says describe the energy changes. So we've got KE here, and that changes to GPE at the top. It momentarily stops moving at the top, and then as it comes down again, it picks up KE. Okay. Part B says calculate the initial KE. Let's do that. KE equals a half mv squared. So that's a half times 0.6 times 2.6 squared. So I'm going to quickly use my calculator. 0.5 times 0.6 times 2.6 squared, and that gives me an answer of 2.028 joules. C, calculate the final GPE. Now we're going to assume no energy is lost here, so the KE at the bottom, yeah, KE at the bottom must equal the GPE at the top. So we still have 2.028 joules. Okay. How high does the ball go? Well, we can equate that to the equation for GPE. M times G times H. You'll notice there is the height, so we can work out the height now. Substitute the values in. 2.028 equals the mass, which is 0.6. Take G as 10, and we can calculate the height. Rearrange the equation. Is 2.028 divided by 0.6 times 10. So we get the height, the maximum possible height, as 2.028 divided by 6. And that equals 0.338 meters. So it's not very high, is it? 0.338 meters. So 33 centimeters. Bit of a weedy throw. In real life, the height would be less. Why? Because there would be some energy lost, energy dissipated, okay, to surrounding. Okay, let's move on to the next one. Okay, child on a swing. Describe the energy changes. Well, we had done that already in an earlier question. B, where does the child have maximum speed? Well, in the middle here in the center. That's where they've got maximum Ke. What is the maximum Ke of the child? Well, we're given the mass and we're given the velocity. So we're going to use this formula again. Half mv squared. Ke equals a half times 35 times 2.6 squared. Okay. So putting all that together, 0.5 times 35 times 2.6 squared equals 118.3. What am I doing? Let's get the rubber. Okay, 118.3 joules. What is the maximum GPE? Well, no energy is dissipated, so it's going to be the same, isn't it? 118.3 joules. What is the maximum vertical height? MGH equals 118.3. GPE equals that. The mass is 35 times 10 times the height equals 118.3. Rearrange the equation. So the height equals 118.3 divided by 35 times 10. And this is equal to 0.338 meters, which is about right. Okay, let's move on. Question 5. This is a log flume has opened at a theme park. The mass of each log and 4 occupants is 363 kg. There's some information. The height of the tower is 37. Assume no energy changes. Okay. Describe the energy changes. Well, at the top here we've got GPE. As it goes down there, it picks up Ke, and then as it goes into the water does work on the moving log, and the energy is dissipated as heat, and eventually the log comes to a stop. B, what is the GPE at the top? GPE equals m times g times h. So that's 363 times 10 times the height, which is 37. Let's work that out. 363 times 10 times 37 equals, big number, 134,310 joules. What is the max Ke? Well, there's no energy lost, so it'll be the same. 134,310 joules, it'll be the same. How much work is done by friction in the water in order to stop the log? Well, we know that work done by friction must equal the loss in Ke. So we've got force times distance equals 134,310. We know what the distance is, 26.2. So the force equals 134,310 divided by 26.2. So let's work that out. 134,310 divided by 26.2 equals a stopping force of 5,126. I'm going to round it there, newtons. Okay, let's move to the next one. A bungee jump, 30 meters up. A woman of mass 60 kg does a bungee jump from the top. The bungee rope has a spring constant of 45 newtons per meter. Assume no energy loss. Describe the energy changes. GPE at the top becomes KE at A, and that all gets stored as elastic potential energy at B. What is the GPE of the woman at the top? Okay, so GPE equals mgh, so that's 60 times 10 times 30. Okay, so 60 times 10 times 30 is 18,000. I could have done that without using a calculator. What is the maximum extension for C? So we're going to use the formula for elastic potential energy, and that's going to be equal to the GPE. Half K E squared equals 18,000. So we know what K is. It's a half times 45 times E squared equals 18,000. So we're going to get E squared equals 18,000 divided by 22.5. 800, yeah, because half of 45 over here is 22.5. So E equals square root of 800, which is 28.3. Okay, there's the answer to that one. Question 7. I like this one. A Roman catapult relied on a heavy mass falling onto a pivoted beam so that a smaller mass would be launched into the air. A mass of 200 kg is allowed to fall 3 meters. So that's 200 kg. It's pretty big. Some pretty beefy Roman soldiers to get that to the top. Was falling by 3 meters. Energy changes. Well, it had GPE at the top. It has KE at the bottom. This then has KE, and then that gives that GPE as well. How much GPE did the mass have before it falls? So B GPE M times G times H. So that was 200 times 10 times the height, which is 3. Okay, so that's 200 times 10 times 3 is 6,000 joules. C, what is the largest mass it could launch over a 10-meter high wall? Okay, so we're going to have GPE up here equals the GPE here because no energy is lost. So we're going to work out some mystery mass, M times G times the height, which is 10, equals 6,000. Now, of course, G itself is 10, so that's M times 100 equals 6,000. Therefore, M must equal 6,000 divided by 100, which is 60 meters. So the Romans were able to use this to launch, oh, hang on, sorry, not 60 meters, 60 kgs. They were able to launch a 60 kg mass 10 meters up in the air with this. No, that's not bad. Question 8. A sledge of mass 200 kg with a mass of man of mass 80 kg on the back of it is pulled by 6 dogs. Each dog exerts a force of 20 newtons. 6 dogs, so 6 6 times 20, 120 newtons altogether, and the total mass here is 280 kg. The energy changes, well, work done here by the dogs equals the gain in Ke of the sledge. B, that was A. What will be the kinetic energy? Well, Ke equals a half mv squared. But that's not the way to do this, because go back to A. In fact, what we have to do is to calculate the work done. Now, I'm just looking at this to see we do have a distance in the question there. So work done equals force times distance. Well, that's 120 times 15. 120 times 15 equals 1,800 joules. And that is equal to the gain in Ke. Okay. Now we could take this further and you could work out the final velocity of the sled, but the question doesn't ask it, so we'll just move on. Question 9. Is a container being dragged up a slope in a loading bay? Calculate the energy dissipated against friction. So now we are not assuming that all the energy is conserved. Describe the energy changes. Well, we've got work done by motor equals the gain in GPE, because this is sliding up the ramp, plus thermal or heat lost as friction due to friction. Okay, that was A. B, how much work is done? Okay, well, work done equals force times distance. That's equal to 1,000 being pulled up the ramp times 15. So that's 15,000 joules of work is being done. What is the gain in GPE at the top? Well, mgh, the mass is 200, g is 10, the height gain is 6. So we've got 6 times 10 times 200 is 12,000. So what is the energy dissipated against friction? Well, we know that 15,000 went in, 12,000 gained in GPE, therefore 3,000 lost as heat. Yeah, and that's because 15,000 minus 12,000 equals 3,000. Okay, so quite a nice little question, that one. Okay, this one, the final question. A barrel weighs 500 newtons. Here it is. It's being rolled up a ramp onto a van. So we're looking at two situations here, situation 1, situation 2. A second barrel of the same weight is lifted onto the back of the van, which is 1.2 meters off the ground. So either you can do a direct lift, which is method 2, or you roll it up a ramp, which is method 1. Energy changes. Well, the work done lifting equals the gain in GPE. We're going to ignore heat loss in this. We assume that no energy is lost. Calculate the work done in each case. Work done equals force times distance. Situation 1, it's going to be work done equals 280 times 2.5 meters. So 280 times 2.5 is 700 joules. Situation 2, got the same work done equals force times distance. Work done equals 500 times 1.2. 500 times 1.2 equals 600 joules. Do they gain the same amount of GPE at the end? Yes. Both gain same GPE because they're both the same height and they're the same mass. Which is the most efficient method? Method 2, direct lift, because it only took 600 joules to raise it. The other method was 700 joules. What is the advantage of the slope? Well, less force needed. So you're not going to break your back rolling a barrel up a ramp, whereas you might do trying to lift it. Okay, so that's the advantage of a ramp. It's a simple machine. It is less efficient in the long run. Right, well, thank you for listening. Work through the questions on Desmos one at a time. Okay, I wish you good luck getting all of these done. I look forward to seeing your answers.